Hello, my name is Rez. I am a professional game programmer and I do electrical engineering as a hobby. And for day 4, I thought I would pull this out into a technical video because this starts to get really interesting with this device. It is a low power, as it says here, low voltage audio amplifier. It's just an op amp. That's all it is. I thought it might be some kind of like radio frequency thing. I was overthinking it because I started hearing radio sounds, but that is not at all what it is. It is literally just amplifying what is around us. So that's it. It's just a simple op amp. If I scroll down, you can actually see the schematic for it. And this is a pretty classic op amp schematic. There's nothing that jumps out at me here. This is usually what you see is you see this sort of Darlington pair coming in. Same thing here on the non-inverting input here, the inverting input here. This is looks pretty much like other op amp schematics that I've seen. So it seems like a pretty standard thing. And here is the pinout for it. So there's one op amp in this thing. It's got a couple of like gain and bypass things that you can twiddle. And they just, as you throw in stuff in here, they're just part of these like voltage dividers. So they just change the underlying like circuitry within the op amp. But that's not something that we're screwing with in this. We've just left pins 1, 7, and 8 floating. So we'll focus on just the basic op amp for this particular talk. Um, Op amps are powered, so that's why we have this pin 6 is VS and pin 4 is ground. So VS stands for voltage, the voltage, source voltage, the power supply voltage. That's all that is. And here, of course, they talk about what those pins actually do. So our non-inverting input versus our inverting input, these are the inputs going into the op amp. And we're just letting it kind of run away, right? We're not trying to do anything crazy with it. We're just throwing an input in it and grabbing the output. That's all we're doing. So this thing's going to basically slam into its highest gain that it can deal with. And somewhere in here, yeah. So they have a couple of circuits here. Largely, this is the circuit that we've built. This is not actually that far off. This is the minimum part count that can be implemented. The gain is internally set to 20. There it is. That's our gain. So that's just part of this. And what we have here so this is most of what we've actually done. So we have power here. In here, they just have a straight up like voltage divider with this potentiometer. We don't have that. Ours is just connected to nothing. We're just picking up ambient things. And the output they basically have a little filter here and connected to the speaker. And we're largely doing the same thing. They have an additional filter here. So this filter helps with high value signals and stuff like that, or maybe low value. I'd have to do the math to figure out exactly why they've chosen this particular value. We don't have that. We have this, although ours isn't 250, ours is 100. But it's the same. This is basically the circuit that we've built. And I will rebuild it with our own actual values. So what this might look like, and I'll wire everything up. So we've got our battery here. And this would be our 3 AA batteries. This gives us 4.5 volts. And this is going to come up like this over here. This one will come down like this over here. And this triangle symbol is what we usually use to define amplifiers, especially op amps. So that's our op amp. And our op amp is going to have an output, which is going to go out here. It has a power supply. Usually the power is here and here. They kind of put in these areas. So this is our power supply, and we're just, we tie this guy to ground. This is our power supply for positive, and we tie this guy to the positive rail. Right. So this is our positive 4.5 volt rail. We have our inverting input down here. We're going to have our non-inverting input here, and I'm drawing them like this because this guy ties directly to ground as well. That's all we're doing. This ties to nothing. It just floats. This goes to our capacitor, like this, comes out here. Here's our speaker. And this is our 100 microfarad capacitor. This is our speaker. Oops. And we have the other side of our speaker, of course, also connected to ground or, our negative rail. So we kind of do this. There we go. This is our output. This is the entire circuit. Now we have noise all around us all the time. So this noise, which is quite small, right? It just looks like this. On the output, now all of a sudden looks like that. We can actually see it. A gain of 30, as it says, or 20, or whatever the schematic said. Now, why do we have this capacitor in here? Well, the problem is we have it's writing this sort of DC output, right? So we have this, if 0, let's do this in a different color. If 0 volts is here, what we're actually going to have is we're going to have the signal up here. Right, its lowest point, like it's going to be within this envelope. And that's not going to work for our speaker. What the capacitor does, in this case, it's a filter capacitor. It's going to filter out the DC part of this, the direct current part of this. So if I come back down here and I go to 0 volts and I create this line, after the capacitor, it's going to look like this, right? It's going to be in this area. It's filtering that out. And if you want to get mathy about it, the actual formula for this is X of C, which is the reactance, equals 1 over 2 pi FC. So in other words, the reactance is the impedance or the effective resistance, how much this resists the flow of current. That's what the reactance is. And it changes based on frequency and, of course, capacitance, inversely. Which means, in our case, the thing that's changing is frequency. As frequency goes up, reactance goes down. With frequency super high, that capacitor will look effectively like a piece of wire. It'll just look like a short. It'll look like just a piece of wire. With frequency really, really low, that capacitor will look like a very high value resistor. If frequency is incredibly, like let's say that in this sort of example, frequency equals 0, right? In other words, we're in DC land. If frequency is 0, what are we going to get? Nothing. X of C is going to be approximately equal to infinity, which is, of course, what we see. That's why when we set it up, something like this, where we have, plus 4.5 volts, this comes down to our, we'll create a little resistor here. This comes down to our LED. If we were to put a capacitor here, like this LED will light up and then slowly dim. We saw that earlier in a previous day. That's what we would see, because this guy here acts like an open circuit. It acts like as if you had pulled a wire out. It takes a while to get there because it has to charge up. So there's some delay, but it will act like that in this world. Likewise, if we flip this around and we say, okay, well, what happens if frequency is effectively infinite, like this theoretical infinite? I cannot draw infinity symbols, right? This infinite frequency. Well, great. X of C is going to be approximately nothing, right? As frequency approaches infinity, X of C, our reactance, approaches nothing. So the whole point of this is to say, okay, we're going to filter out the DC part of this. And yes, we lose some of the signal, but we're mostly just filtering out the 0 volt side of this. So this is a filter. It's a way for us to filter out the DC and have only the AC, the alternating part of this. capacitors really, really don't like DC in that sense. So that's the whole point of this circuit. What's going on here? We're just taking the signal, cranking it up, and then filtering out the DC so that we can have the speaker be able to actually play what's going on. So that's the point of all of this. Now, going back to this guy right here, we can see that we've more or less built that same, or their sample here is more or less that same kind of thing. Now, it's interesting that we don't have a filter here. And it's interesting that, like, this is more common of what I think you'll see. This sets the gain to 200. They do some internal stuff with it. This is how they're using, like, the bypass and how they're using the gain set. So you can sort of set the gain by setting components within, where is it? Within these, like, pin 1 and pin 8. That's what's going on down here. Where was it? Down here. Right, pin 1 and pin 8. There it is. We've got a 10 microfarad capacitor here. So my suspicion is that we may end up getting more capacitors. We might get, a 10 microfarad or whatever they want to use, some little ceramic disc capacitors, and that we might end up using those to then tweak the gain and set the gain of this amplifier to some other value as we do something like this. Perhaps even variably set it, which is what I think we're actually going to get to, is that we'll set this with a variable setting, more or less. But it depends on what we end up doing. We can also do a lot of interesting tweaks and stuff, so I'm really curious where this is going to go. Okay, we're back at the bench. I wanted to show one last thing here, just to kind of show how this all works. I have connected the oscilloscope, and this purple trace is before the capacitor. So it's before it's right on the output of that amplifier. The yellow trace is after the capacitor, so it's on the other side of that. So if we look here, the purple trace is going to be right on this pin, right at the output. Whereas the yellow trace is right on this speaker here. So we can watch that filtering of the capacitor happen. So I'm going to turn on the power, and you can see the purple jumped right up, but the yellow is staying the same. Note this purple triangle, this is the 0 volt range. This is 0 volts. So if I'm touching this thing, you can see they have the same kind of signal, but purple is offset, has this DC offset. The yellow one does not have the DC offset. And purple looks smaller because I've set it to 1 volt per division. But if I set it to 500 millivolts, which is what they both are, so now they're both the same. But that's what's going on. That's why we have the capacitor there, to get rid of this DC offset. I mean, we're way up here now, right? This is so we're down here, so yeah, we're way up there. And so we want to filter that out so that the speaker can actually play it. So that's the whole point of that. And for fun, I've set up the purple guy who's here. Again, I've set him on the input now. So I've set this up on the input. So in this case, I've literally connected it here to this red wire, just so that we can watch the amplification happen. Now, in order to make this work, notice that the yellow one, and I don't know if that's even really coming through, but my yellow trace is set to 500 millivolts, so half a volt per division. So each division is half a volt. Here I've had to set this to 2 millivolts per division. Suppose I could set it to 5. So purple is now 5 millivolts per division. It's now 100 times smaller. If I touch this, now you can kind of see they sort of coincide. Mostly. I wonder if I can set this to 50. There we go. Now it's 10. I can't, there's no, I can do 20. They'll be about similar sizes. Because remember, it's a 20x increase. But yeah, you can kind of see it. I'm not getting as much as what I got before because I'm getting interference from the oscilloscope itself. But you can see the amplification that happens. If I were to actually set these to the same values, I mean, now they're both 500 millivolts. I mean, you can't even see anything on the purple trace because it's so small. But if I set this to like 100 millivolts, yeah, you can see it a little bit. So, but if I set, we'll go to 50. Can I set you to 50? It's probably not even really worth setting this to 50, but because it's just going to overpower. But you can see that's the amplification, right? They're both set to the same millivolts per division. So it's, that purple signal is getting amplified to that to that yellow signal. So that's it. Okay, I'll see you all tomorrow.